Okay. In that case, let me start by telling you a little bit about about social networks and graphs in general. Again, we're not going to talk yet about specific mathematical models or anything, but just in general, what are networks? Where we find them? Why are they interesting? Why do we care? And the different sort of broad categories of networks that we can study in many ways. So I prepared this class to focus a little bit on social networks just because it's cool and everybody sort of likes to think about them these days. So when I think about social networks, I usually think about Facebook, Twitter, LinkedIn, Instagram, WhatsApp, WeChat, Snapchat. I easily lose track of all of this. The idea of a network is we have players or individuals or agents or people, whatever it is that we're talking about, and we're creating connections among each other in such a way that those connections say something about how information passes, how opinions propagate, how Twitter messages go around, and all sorts of things. The study itself of networks doesn't have to be social networks, can be many other things. Some of the really cool problems that I like to think about is networks related to the internet and the web in general. So let's see if this works. So the internet and the web, but as I said, I'll focus a little bit later as we go along on the social aspect of networks in general. Now, so what exactly are these connections that we're talking about? Well, if we're talking about a social network, the connections are happening among people. And what exactly that connection means depends a lot on the network you're looking at. For example, in a Facebook network, we can think about the links that are connecting people as the friendship, right? Friendship among different people. You're friends with me, then you were connected. But when we're talking about things like the web graph, which is the network formed from the web pages on the internet and the links that go from one web page to another, then the edges could represent, for example, hyperlinks that tell us where to go. If you're thinking about a Twitter network, then you could think about the relationships being between the follower and the followed, whoever is sending messages and that kind of thing. Of course, there's a lot of networks out there, very interesting, that have nothing to do with people, right? You can think of the internet at the router level, so at the computer level. It's sort of a physical network. You have computers or servers, and they're literally connected by big, thick wires, one way or another, or sometimes just Wi-Fi connections. But that sort of has nothing to do with people in general. We could also think about networks that are made from neural connections in the brain. I've heard many interesting talks and ideas about how to study the brain using the idea of networks. We can think in biology, we'll look at interactions between proteins. And again, how exactly they interact creates a kind of relationship between the two parts. We can think about citations. If you're interested in writing an article and see who's citing your work, that define something we call a citation network. And in general, they can name a billion different examples of networks that are out there that tend to be very big. And when I say big, sometimes in the millions and billions of nodes. So these things can be really, really massive. And what we're trying to do with them is we're trying to draw some insight, some interesting things of what's happening on them. So one way that to do that is to think about many of these networks as graphs in particular. And here's where we're going to start using a little more mathematical terminology to refer to what we're going to be working on. So a graph in particular consists of a set of vertices or nodes. These are my individuals, my agents, my people, my computers, whatever it is, and a set of edges. Okay? And the edges are going to refer to the connections between the vertices, between the nodes. Now, graphs in general can be either undirected or directed. What does it mean to have an undirected graph? Well, it means that the relationship is not, the direction of the relationship is not important. So if we're friends on Facebook, then I am your friend, you are my friend, and it's a symmetric relationship. We both sort of affect each other in the same way. On a directed graph, Think about the web graph where I have a website that I'm looking at and it has hyperlinks, but the hyperlinks are directed. They're taking me somewhere. It does not necessarily mean that once I get to those other web pages, that those web pages will have a hyperlink towards me. So again, directed, usually we can use it to model different kinds of interactions. When we have an undirected graph, as I said, the relationship is symmetric. In a directed one, sometimes some of the vertices can be, some of them may not be. In terms of notation, we usually call the vertex set, just to be general, I'm going to say it's the numbers 1 through n. Can get more interesting with the labels, but here the labels are just very simple numbers. And we're going to write the notation I connected to j to mean that there is an edge from I to j. If this is a directed graph, usually we think about those edges as directed edges. Another thing that's going to pop up as part of the interesting things to study on a network is the degree of vertices. So the degree is the number of neighbors, in other words, or the number of edges that connect to a specific vertex. In a directed graph, we have two different kinds of degrees. One is going to be counting the number of neighbors that are coming into us, that are inbound neighbors, and that's going to be called the in degree. And the other one is going to be counting the number of outbound neighbors or the connections that are coming out, and that's going to be called the out degree. And as you will see later, these are important things that normally we focus on when studying graphs and networks. So just to go back to some of those examples that we're all very familiar with, the internet, computer to computer, that's usually thought of as an undirected graph where the vertices are the servers or the computers and the edges are the connections, usually physical in some sense, either Wi-Fi or an actual cable. We have the web graph. That's another very, very large and very important network. That's the websites that are on the internet. So this is a directed graph where the edges are corresponding to the hyperlinks from one place to another, from one web page to another. We have social networks like Facebook, where the edges represent friendships and the vertices are people, so, or at least some of those are people. We have other graphs like Twitter, where again, it's the vertices are people, and the edges, depending on, there's several different kinds of graphs related to Twitter. Some that have to do just with, I'm a fan, I follow you, and I follow everything that you say. So that creates edges between followers and followed. There's other kinds of Twitter graphs where you're following the texts or the messages themselves and the retweets and that kind of thing. So in this particular example, I chose just the people, and then I follow you, you follow somebody else, and you have a chain. Another example would be a citation network where we have scientific articles that are being published, and as new articles come along, then we cite existing articles out there, and we are creating directed edges by citing those as we go. Just to give you a cool picture of some networks, I always like to show some different kind of depictions of a graph. We'll talk about this later next week, but depicting a graph is not necessarily something easy to do because there's many ways of doing so. This graph over here, you can see it. I like it because it's cool. It has some vertices that have neighborhoods that are very, very dense. These are basically nodes that have, if I open it up a little bit, nodes here that have many, many neighbors, but those neighbors don't tend to go anywhere. And then we have another center here of vertices that none of them are particularly high degree, but they are connected to each other. This one over here is a famous depiction of the internet from several years ago that makes it look really cool. This is the internet at the router level, at the physical level. And this is a picture of a tree that at some point I ran into that has some, again, this feature that there are some vertices that have a lot of neighbors and other vertices that just have like typical number of neighbors kind of thing. So you can imagine that how we choose to represent our nodes on a graph can say a lot of things of what we're looking for. So let me start by talking about the different kinds of graphs that we have and some of the attributes that we usually look at about them. Let me start with undirected examples only. All of these have their directed generalizations. We say that a graph is simple if the graph has only at most one edge between any two vertices, so just one, and it has no self-loop, so nothing like that, right? No edges of a vertex with itself, and only one between any two vertices. So this is what we call a simple graph. In the directed setting, the same thing applies. We must have at most one edge in a given direction from two vertices, but here we can have one edge in one direction and the other one in the opposite direction. So for example, something like this, where I have both directions, that's still simple because it's only one edge that goes from this node to this one and one edge from this node to that one. So that's a simple graph. The opposite of a simple graph is a multigraph. In a multigraph, in the undirected case, what we are allowing is we can have multiple edges like these ones between the same two vertices, and we can have self-loops. And you may wonder, why is it that we have multigraphs? I mean, just think for a second about your typical web page on your campus website. You know, many times what you see is you have the page itself that has the same hyperlink at many different positions. So if you think about just counting the hyperlinks, you'll see that there's many hyperlinks that are actually going to the same place. So you would have several edges between the same two vertices in the same direction. So in the directed setting, if I put one edge here in this direction, this is still a single edge. But if I have, let's say, two in this direction like this, that's a multi-edge. The self-loop, doesn't matter in which direction I write it, it's still a multi-graph if we allow to have those. What other types of graphs can we, or attributes of graphs can we look at? Well, we usually think a lot about the connectivity properties of graphs. So in order for us to talk about connectivity, let's define first what a connected graph is. And as its name suggests, as you can see, a connected graph is such where for any two vertices, there is a path. Here, there's one edge. But if I choose this one and this one, doesn't have to be an edge. It can go, as long as there is a path, I can get there from one vertex to another in a path of a certain length. Again, doesn't mean that that the edge has to be there, just that there's a way. So if I want to look at this two nodes, well, I could say this is my path. And that connects the two. And a disconnected graph, different things can happen. The most obvious one is I can have isolated nodes, right? Where those nodes are simply have no edges, and therefore there's no way to get there or to go anywhere from those. So that's easy. So sometimes we prove that certain types of graphs are disconnected by just showing that these guys are there, like the singletons. But that's not the only way in which you can be disconnected. You can have subsets of vertices like this one over here that among them they are connected, but they are disconnected from this set, right? So there's no way that I can go from these vertex to this or from here to that one. However, I can go between these two. So you can see that disconnected covers a lot of many different pictures of what a graph can look like. When it comes to directed networks, the notion of connectedness becomes a little bit different, a little more subtle, because then we have different degrees of what we say are, what we think of connectivity. In a directed graph, the term that plays a role, as in my previous example, is something we call strongly connected graphs, right? Or strong connectivity. And what it means is, again, if I take two vertices in my graph, I'm going to find a path, directed path, that goes from this one to, well, from this one to this node in some direction. And let's find that path. So to get to that path, my path is go here first, then come down here, then go down there, and then here. So I can get to those, right? If I choose these two vertices here, I have to go around here, you can see, because the other edge is not allowed. So I can do that. And then I need to require the opposite in the other direction. So if I want to go from here to there, then I can come this way. get there. So for a graph to be strongly connected, we must have a path from any vertex I to J, but also from J to I. Now, these paths don't need to be the same. They could be completely different, like in the example that I have here. Besides having the notion of disconnected, which we also have here, which means those singletons or sets of vertices that are completely isolated from other sets, we also have this other notion of intermediate connectedness, which is called weak connection. And what it says is that the edges exist. So if you can see, if you ignore the direction of the edges, then this graph is connected because I can go from any 2 points to from any vertex to any other vertex in the graph. In that sense, ignoring direction is fine, and I have a connected graph. However, if I don't ignore the direction, then I can't actually get from one place to another. And the example here, for example, that I depicted is if I'm in this vertex, I can go here, right? But if I'm in this vertex, there's no way for me to get there. There's no edge. So these vertex is not reachable from the set of vertices inside. Same thing with this guy over here. It's weakly connected because there's a path, but the path is not directed. And as you can see, since there's only one edge going into this vertex, there's no way that this vertex can go anywhere. So this vertex is isolated. Once you're there, you can't go anywhere. Now, what I indicated here in this subset is what we call the strongly connected component. A component is going to be a subset of vertices that are and their edges that are all sort of connected. That subgraph is all strongly connected. So as you can see, among these vertices, I can go from here to here, from here to here. And since I have the cycle, everybody is reachable from those. However, the three vertices that are out here are not part of that strongly connected component. Any questions so far? Okay. What other types of graphs we'll probably talk a little bit about? This is something we call a regular graph. And in a regular graph, all the vertices have the same degree. They all have the same number of neighbors. So for example, in this particular graph that I have in front of me, all the vertices have degree 2, right? 2 edges for each one. Doesn't mean that it has any particular shape. It just means that every single vertex in the graph must have the same number of edges. I can decompose it. I can make this into a circle. So you can see, you can untwist this little fish that I created and you can get other forms. It doesn't have to be a cycle either. But the idea is you just count the number of neighbors on each vertex and you have a regular graph. And we have a similar concept for directed graphs. Again, when we're looking at fixed degrees, in degrees or fixed out degrees. This is what we call a complete graph. In a complete graph, I have an edge between every single vertex and all other vertices. So every single possibility is there. So for example, this vertex has an edge with this node, this one, that one, and this one. So all my vertices, or all my possible edges are there. If you think about how many edges there are, well, if I have 1, 2, 3, 4, 5, right? 5 nodes, then each of these nodes is going to have to connect with its 4 neighbors. So you can see the 4 edges that each of those has, right? So that's a complete graph. And when it's inside of a bigger graph, this kind of structure, we usually call that a clique. We'll get to that today. Another interesting kind of graphs are something we call bipartite graphs, where nodes or vertices come in different classes. So for the bipartite case, I have 2 classes. We have other options where we can have many classes, of course. So in a bipartite graph, you can think of some of the vertices being, let's say, movies, and some of the vertices being actors. So each actor is connected to a movie they acted in, But the actors, they're not directly connected among themselves. So there's no edges between these red vertices, which are the actors. There's only edges between the actors and the movies. There's also no edges between the movies themselves. So there's no edge between the movies. There's only edges between the movies and the actors, as you can see. Now, I try to depict it in this way just to look sort of interesting. However, when we think about bipartite graphs, there's always a way of transforming something like this into something like that, where I have on one side, let's say type 1 vertices, on the other side, the second type of vertices. So here are my actors, and here are the movies. And as a matter of fact, these two graphs that I depicted here are exactly the same graph. And to see that, you can see that, let's say that this is my vertex number 1. This is vertex. So if we order them like this, is 1, 2, 3, 4, and 5. And these are A, B, and C. Well, 1 has to A and B. So 1 has to A and B. This is 2. 2 has to A and to B. So A and B. And you can follow the example to see that these two graphs are actually the same graph. However, sometimes you see something like this and it's not obvious from the picture, the way we decide to represent the graph, then you could have like the two classes all sort of intermingled. So now that we've seen the basic ideas of the types of graphs that we might want to study or that we might want to think when analyzing real world networks, let's talk about some of the structures that are interesting for one reason or another. So one of the structures inside of a graph that often gets a lot of attention is the cycles, or counting cycles, or looking at the length of cycles. So what are cycles? Like, cycles are paths that travels throughout many vertices without repeating any vertex, and that end in the same place where they start, right? So cycles are important because they tell us, and there are many interesting questions about them that tell us, you know, how long it takes us to be able to go around and come back to where we start. And the length of the cycles is one of the characteristics that we tend to study. The number of cycles is another. And in general, this is one of the things that if you ever are interested in reading about graphs in general, you'll see that we pay a lot of attention to that. We also have cliques. And cliques are these complete subgraphs. The simplest clique is a triangle, so everybody is friends with each other. If you think about this in the context of social networks or networks of people, you can think of cliques or subsets of friends that are all friends among themselves, right? So if I have a big group of friends that has 20 people, but not everybody gets along with everybody, but there's certain subgroups of 3 or 4 that all of them are friends of each other, that's my clique. And again, this tells me something about the community structure, about the strength of the connections among certain groups more than others, and that's why we're interested in those. Another thing that we focus quite a bit on is what is the distance between two vertices? And by distance here, I mean the minimum path, so the length of the minimum path connecting two vertices. Why? Think about the internet and sending an email through the internet, right? You are in one computer, wherever your hometown is, and you're trying to send an email to somebody across the globe. Well, you're going to have to find a path that gets you there, right? And it's important that in order for your email to get from wherever you are to, let's say, Australia far away and potentially the other side of the world, you want the path not to be very long. And you would think, well, there's nothing connecting me to somebody in Australia directly. And I'm pretty sure there's no big wire that connects, you know, the United States with Australia in one go either. So how do you get this distance? Well, this distance is attained in different ways by sort of finding paths among certain types of vertices. And it's very important in terms of describing the connectivity of a graph and the properties of the graph when it comes to communicating from one side of the graph to the other. Another thing that we look at is the components of a vertex, and the component of a vertex are the set of nodes that you can reach from one particular vertex. So in some of these examples that I had before, this is just all one component because from every single node, I can reach all the others. However, in my disconnected example, this is one component because these four vertices can reach each other. This is another component, and this is a third component. So I'm gonna take a quick moment to just answer a couple of questions. So one question that I see here is, how do I identify a subgraph in a graph? And does it have to be a cycle? No. Oh, so how do you identify a subgraph? Is defined as a subset of vertices. So if this is my entire graph, a subset of vertices could be, for example, these four nodes, right? So, and a subset of edges. I could say these edges. That's a subgraph, right? I just chose some of the vertices and some of the edges. And it's inside the other bigger graph. That what I just did is actually not a cycle because I chose it in particular to be to be not too close, right? It doesn't close on this edge. So it's not a cycle. So this is also a subgraph, for example. I take these two vertices. As a matter of fact, this one with this one is also a subgraph, right? So does that answer your question about the subgraphs, Diana? So another question, the next question says, are the clicks cycles? So here's a click. This is my 5 click. The clicks themselves are talking about also the edges, right? They're talking about the existence of edges. So is there a cycle in a click? Yes, this one, right? There's a cycle. So there's one. So in a click, there will be a cycle because you can always just connect them all because you have all the possible edges. But we think about the click itself as not just the cycle itself, but all the edges that connect everybody else. So those are slightly different concepts. Does that answer the question, Abril? Great. So the next question says, if a connected graph does not have cycles, can I divide it into subgraphs? So if a connected graph does not have cycles, can I divide it into subgraphs? And it's a connected graph that has no cycles there, right? I mean, there are cycles. This one I have that I draw. I did not draw any. No, there's the cycle. This one, this one, this one, and this one. So I'm not sure I'm following the question. I guess let me try to address the subgraph part instead, because I can always define a subgraph, right? It's relative to what I'm interested in. This over here is a subgraph of the bigger graph. So if that's what I understood, I think Jonathan was talking about the, let me read it. What you can do is to take the graph G and divide it into a graph with no cycles. That is what is known as a tree. I can always do that. I can always sort of choose the subgraph that has no cycles, if that's the question. I'm not sure if I understood the question properly, but if you want to reword it, I'll be happy to try again. So let me move on to the next question. It says, how many total cycles are there in a K-click? That I will need to think about it. So I'm going to skip that one for now. Okay. So here's a click. Okay. So let me move on then. I will take a click question at the end since I wasn't planning on counting those for now and I need to get something else, but I'll be happy to come back to that. So we were talking about cycles, clicks, distances between vertices, components of a vertex. Those are some of the structures that we look at. Other properties that we study when we look at graphs can be the diameter of the graph, which is the maximum distance between two nodes. So I take two vertices in the graph, I find the shortest distance, and I'm trying to find the longest of those shortest distances. That's what we call the diameter. And again, this is an interesting property that tells us about how well connected the graph is. The component sizes can be a very interesting question to study. In the component size, normally we focus first on who is the largest one, which is the biggest component. So the component that has the largest number of vertices. And then we're interested in looking at the smaller one. So is the second component as big as the first one? Is the third one, you know, reasonably big, or are they getting smaller and smaller? So when we look at components, oftentimes we're focusing on the sizes. I'm sorry, there's music outside. There's Mario Brothers music outside. Hopefully you don't hear it. Another question that we can look at is this length of cycle. So what is a typical length of a cycle? So if I start from one vertex and I start moving around, looking for other nodes to go to, and one at a time trying to come back, it might be in some graphs that I can come back very quickly. So in a graph where I have lots of triangles, I can come back like this. In a graph where in a directed graph where I have bidirectional edges, I can come back first here and then come back in 2 steps. So I can get back very quickly. However, in many interesting graphs, as the ones that we were going to talk about here, it actually takes a long time for us to be able to come back. So the length of cycles is going to be long. And that's a very important property that has some consequences in terms of the things that we can study on many of these graphs. So we talked about cycle lengths, and we can talk about clustering. So clustering has to do with finding subsets of vertices that are close to each other. And the best way of looking at it is through something called the clustering coefficient, which is measuring the proportion of triangles divided by the number of open wedges. So the number of triangles is I give you 3 vertices, and I look at how many of those 3 vertices create a triangle. And then I divide that by the number of triplets where only these edges are there. That's what we call an open wedge, or this one over here. In graphs where there's clustering, the clustering coefficient is going to be higher, and it means that there's bulks of vertices that are close to each other. In graphs where we have no clustering, then there's not going to be that phenomenon of having closer vertices. They're going to tend to be more spaced out in some sense, and in general, what we could see is the cycles are going to get bigger, and the density of vertices close to each other is going to be sort of uniform across the graph instead of being denser in certain parts. So this is very important when we look at graphs where we're trying to identify vertices that are common, that have some characteristics in common, that belong to a same community, that have the same interests, that tend to look at, you know, to watch the same kind of movies. In that kind of setting, the clustering is sort of something, the communities and the clustering together have something to do with being able to identify the vertices in a graph that have things in common. So in terms of the questions that we're going to be posing when studying graphs, and in particular large complex networks, we're going to be thinking about connectivity issues. And specifically, if the graph is undirected, we're going to ask the question, is my graph connected? Right? Why is that important? Again, if you think about the graph being a model of the internet, if it's not connected, it sort of defeats the purpose of having it. Right? If you're going to be sending an email and that email is not going to be able to reach certain parts, then it sort of doesn't work as a network that connects all the different nodes that it has. In the sense of directed networks, we might wonder about, is my graph strongly connected? Can I go from any one vertex to another? Maybe, maybe not. If the answer is no, and it's not strongly connected, then we might want to ask, is there a giant connected component or strongly connected component? What does it mean to be giant? If my graph has n vertices, usually we refer to a giant component if there's a subset of vertices that create a component and that has the size that is a positive fraction of the size of the entire network. That's what we call it to be a giant. And this is important again, because once you're restricted to these giant component, it means that inside that significant part of your network, you have all the connectivity properties that you would be looking for in a connected graph. Just to give you a very important example of something that is not connected, but that has a strongly connected giant, think about the web graph. So in the web graph, that's a highly disconnected network. However, there is a positive fraction of all the web pages in the universe here that are strongly connected. And those form what we call the giant strongly connected component. Once we've identified the size of the largest component, the sort of follow-up question is, how big are the other components then? So the big one has a positive fraction of all the vertices in the graph. Does it mean that the small ones are also big, that the second largest is big, or the third largest is still big? And what we'll see is in many of the models that we work with, actually the answer is no. The giant is big, but the second largest is actually quite small. And the third largest is even smaller. So as we move away from the largest, there's like a big gap in size going down to other components. And those are some of the interesting properties that we often see in random graph models. What is the diameter of the graph? You could be thinking, I have a graph with 1 million nodes or 10 million nodes or 1 billion nodes. Is the diameter big? If the diameter is big, if the internet was big, then your emails wouldn't get to their destination very quickly, would they? Imagine sending an email again from here to Australia. Well, if the distances were proportional to the size of computers on the internet, then we would be in serious trouble. So the diameter, even when the graphs are very big, is not necessarily big. And in big social networks and complex networks from the internet, the web, like that kind of example, it's actually quite small. And that's an important property of these graphs. Another question is, what is the typical distance? Again, this has to do, how many steps is it going to take me to send an email? Through how many servers is my email going to travel before it gets to its destination on average? What is the degree distribution? That means what is the proportion of vertices that have a lot of neighbors versus most of the other vertices that have, let's say, an average number of neighbors? Is my graph homogeneous or inhomogeneous? Are there vertices that are very different, that look very different in their properties and their degree than other vertices? And that's, again, something very, very important when studying complex networks from the real world. Does a graph have clusters or communities? We've talked a lot about that a bit. And the last question that we'll get to on the fourth lecture, if we can, has to do with, are there some vertices that are more important than everybody else? And what I mean by that, by more important, is like, imagine passing on a rumor or spreading out some message. Are there vertices that if you tell those people to spread the message, will actually end up spreading the message through your network faster than if you just give it to other vertices instead? So this question is actually very, very important for the study of networks. And that's one that hopefully we'll get to study later in this course. Before we go into the more mathematical description of some of these models, let me talk about some cool things that happen in large real world networks. The first one is something we call the small world phenomenon. And the story about this is that in the 1960s, a psychologist named Stanley Milgram decided to conduct an experiment. He had many experiments, and he's famous for other experiments that are not related to this one as well. But this one, is now something that almost everybody has heard of. It's called, the idea of the experiment is the following. He lived in Boston, and he wanted to figure out how connected people here in the United States are. How well we know each other, let's say, or, if I give you the name of somebody chosen at random in some other part of the country, how many people separate you from that person, right? How many people in a sequence of acquaintances separates you from that person? And the experiment was the following. He sent letters to a lot of randomly chosen people all over the Midwest of the United States with an address in Boston. So the address of the letter was in Boston. And chances are the person that received the request to send the letter had no idea who this recipient in Boston was. No address, just the name of somebody who lives in Boston. The idea was, the instruction given to these people is just try to help this letter reach the person that is supposed to receive it. And the only thing you can do in order to help this letter get to its destination is to send it to somebody so that hopefully that person that you sent it to has a better chance of reaching the other person. So basically, you're looking for somebody who hopefully knows the person who the letter is addressed to. And by doing that, it turned out that the surprising result is that in the 1960s United States, it took only about 6 people to connect to complete strangers. So I would get a letter of somebody I've never even heard the name, and it wouldn't take that long for that letter to get to the person if I just start sending it to somebody I do know. The idea being, if you think about it, that what would you do? If you had the letter in your hand, who would you send it to? If you think a bit about it, the obvious thing to do is to say, well, I have this friend who knows 1 billion people, right? Very, very popular friend. So maybe that person knows. So you would try to go and send it to this person that has 1 billion friends. And hopefully that will lead to that person, if you're lucky, that friend of yours who's very popular would know that other person, and you would get there quickly. In principle, that's all we need to do. We're looking for those highly influential or central vertices in the network, with the idea that by going through these special vertices, we'll get there fast. And this phenomenon became known as the 6 degrees of separation, or the small world phenomenon. And what's sort of interesting to know is that, as rare maybe at first sight that this might sound, this is actually not rare at all. Most of the models that we have will satisfy the small world phenomenon, and the intuition that I described of why is it that it works actually does hold true in general. The other aspect of networks that we like to think about is scale-free networks. So if we look at the degree distribution, this has to do with those vertices that are really, really, really popular. So if you look at some vertices, everybody on average has, I don't know, in Facebook, I believe the average is somewhere around 300 friends or something like that. But there's people out there who have hundreds of thousands of friends, right? So if you look at what is a proportion of vertices that have degree k, this is what we call the degree distribution. And in large social networks, a funny thing happens. If everybody was roughly the same, we would all have more or less the same number of friends. We would all be a very uniform network. However, instead of everybody having roughly the same number, it turns out that the degree distribution looks like it decays proportionally to a power. So k to the minus gamma for some gamma. Many times this gamma takes value somewhere in between 2 and 3, which makes this distribution of the degree very, very heavy-tailed. That's how we call it. It means that although the average number of users of Facebook has the average number of friends, there's certain friends out there that have extraordinarily large number of friends that are being reflected by the fact that this tail distribution, the distribution of the degrees decays fairly slowly relative to other things. And this is what we call the scale-free property. And those pictures that I showed you at the beginning of the internet had those sort of stars that are representing exactly that. Now let's start getting a little bit into the mathematics of how we're going to study the properties of graphs. And I think we have a few questions, so let me try to see which ones we can do. So I think there was the question about the clicks that got answered. Get back to that later. So I'll skip the combinatorial questions for now, and I'm going to go to the modeling questions because those are the ones that are related to what I want to show you towards the end of the lecture. So the question is, if we choose a friend to send a letter to at random, would we determine the probability of a friend knowing the recipient based on the degree sequence and or the degree distribution of the graph? If the question is, can you optimize it? Yes, that's what protocols on the internet do. There are ways of trying to find those paths a little bit faster. However, this property about the 6th degree of separation is completely at random. I mean, you don't even have necessarily to think about an agent who's making the decision. Those short paths will sort of happen. They're there on the graph. So what the person is doing is just probably thinking at some level, trying to get there faster, trying to reach the hubs, the very, very high degree vertices that connect in short distances the nodes. So if you think again about another kind of network, let's say a shipping network for FedEx or DHL, then you can think, that the way they operate is that you have centers or central hubs that are very, very large places where they collect a lot of the traffic that's coming in. And then once it gets to those big shipping centers, it goes from big shipping center to another big shipping center in one truck that takes a lot of the packages from one place to another. Same thing with airlines. You have Atlanta, you have New York, you have LA, you have certain airports that collect a lot of the traffic into those ports. And then from those big connected nodes, you have short distances. So I'm not sure that the way that Milgram, when he was designing the experiment, he was counting on people trying to find those or know who they were. But we sort of all naturally tend to look for, like if I had to send it to somebody, I would probably already be sending it to somebody who I know. And interestingly enough, knowing the distribution of the degree of the person, knowing that that person has me as a friend, is already very different and very biased. And that helps get those distances short. Does that sort of answer? We'll get to that because that's a very interesting phenomenon. This what I mentioned right now is called the size biasing. And it's the idea of my friends on Facebook have way more friends than I do. And that's a mathematical statement. So we'll get to that, just not today. So we can talk a lot about it later if you want. And if not, I promise to get to that later. So let me give you some tools in terms of thinking about graphs, because we're going to need those for what we're going to be doing later. And for any graph, I'm going to define V to be the set of vertices. G of VE is going to be the graph on the set of vertices with set of edges E. And we're going to encode the information about which edges are present in the graph using something called the adjacency matrix. And the adjacency matrix is an n by n matrix, the size of the number of vertices, that basically just gives me Aij on the ijth component, the number of edges from vertex I to vertex j. If my graph is directed, this is a directed edge, but if it's undirected, we're going to have symmetry happening on the graph, and every edge, if ij is there, so ji is also going to be there. If my graph is simple, then the number of edges is always either 0 or 1, so the entries on the adjacency matrix are 0, 1. If my graph is not simple, then the entries can be integer valued. In an undirected graph, as I said, my matrix is going to be symmetric. And just to give you a quick example, this is the graph and the corresponding adjacency matrix. So vertex 1 has edges to 1 and 4. So it has edges to 1 and 4. Vertex 2 has edges to 1 and 4. So 2 has edges to 1 and 4. Vertex 3 has only one edge to 4. So only one edge to 4. And vertex 4 has edges to 2, 1, and 3. 2, 1, and 3. So here's a graph. I go to the adjacency matrix by just mapping the way that I did. If it's directed, then I might have some edges and not the others. But because in this example, it's an undirected graph, you can see that my matrix is symmetric. And because this is a simple graph, then there is nothing on the diagonal. So there's zeros on the diagonal because those are the self loops. Now, why is the adjacency matrix important? This is not the only way to encode information about a graph, but this one is one that's convenient for many things, because it turns out that if I take the matrix A and I raise it to the kth power, then the ijth component of matrix A to the k is counting the number of paths of length k from vertex I to vertex j. In other words, this matrix A to the k gives me all the number of paths from any two particular vertices. And again, if the graph is undirected, then this matrix A to the k is still going to be symmetric. And again, we'll see applications of why that's important later. I have only a couple more minutes, so I just want to give you a quick introduction of what random graph models are, because we're going to start with that next week. And I like to explain why we need them and what they are. So as you can see, the graphs themselves out there, they're in the real world, whichever you take. And you can think of those from a deterministic point of view. That's my graph, right? That is the graph. It has 115 people in it, and these are the edges that are relating those 115 people. However, if I'm thinking about a social network, for example, well, this 115 is probably more like 115 million kind of thing, and it's a really large graph. So it's not easy to analyze when it's that big. On the other hand, if I'm thinking again on the Facebook graph, well, the graph right now is already different from the graph right now, because edges are constantly changing. People are dropping out, people are befriending people, people are unfriending people, and therefore the graph is constantly changing. So if you're looking at a very specific graph and trying to say something about that instance, whatever you study there might not be what you're interested in the next 10 minutes, because the graph is not the same anymore. So rather than try to think of graphs of specific instances that are unmovable and that's the object that you want to study, we think of the instance that we're interested in as just one example of some larger class of graphs, of which this particular one is just one example. And why does this work? Well, if I'm interested in connectivity, on the distance, the typical distance, on the diameter, on whether it's connected or not connected, imagine that for these larger class of graphs, I could actually prove that my graph is going to be with high probability connected. Well, if I can prove for a larger family that my graph is connected, chances are that my specific graph that I have in front of me will be connected too. If I can prove that the typical distance between vertices is of order 7 steps in a general class, then chances are that my real graph also has typical distances that are of order 7. So many of these properties go way beyond the specific instance of the graph that we're looking at. So there's value in having this random way of thinking about them, where my graph is just one example. So in order for us to think about it in this way, we need to consider the set of random graphs as a bigger family of mathematical models that can say something interesting about the properties that I want to study in my real graph. Now, because this is a model, there's not going to be a single random graph model that can do exactly what your specific graph does, or that is going to look exactly the same every single time. So we often have to choose what are the things that are important to the questions that I'm studying in order to choose a random graph model that can mimic or that can copy the aspects of the graph that you really want and say something interesting about what you want to study on them. So what we're going to be doing in the next couple of weeks is we're going to talk about different random graph models, how we can do those, and how there are different options that do different things, that have different properties. And then I'll show you what we can say about those. So I'll stop here since I think it's 4 o'clock. I'll be happy to take some questions, after this for a few more minutes. But I think this is probably a good stopping point for the class itself, and we'll resume next week. So I have a question about the time. I was told that the session itself was supposed to be 1 hour. Am I mistaken? And that we had some time for questions after? I mean, I can keep going if you want, but if we leave a little bit of extra time at the end, what we can do is we can talk about homework problems, and we can talk about some of the things that we discussed in class in a little bit of a more informal environment. And I think you probably find that more useful than just listening to somebody talk for over an hour on any given week. So if that's okay with you guys, I'm happy to open the channel. Feel free to just turn on your video and we can just talk about things. And we will be posting short assignments after each class. The first assignment that we prepared has only a couple of questions, so you can sort of test some of the concepts that we've been looking at, and we'll send instructions about that later as well today, of how you can submit your assignments so that we can take a look and grade them. Assignments are optional, so feel free not to do them, but I invite you. They're not supposed to be hard. They're supposed to just get you comfortable with some of the concepts, so that as we go deeper into the mathematics, we can stay together and you can get something out of this. Okay. If you want to stay and just chat, what I'm going to do is I'm going to turn off the recording so that you can feel free to say whatever you want. And we'll see you next week.